There is a star 190 light-years from Earth that should not exist. It's not exotic, it's not spectacular. It's a dim, yellowish subgiant in the constellation Libra. You can almost see it with the naked eye, barely. Catalog number HD 1400283, but astronomers call it the Methuselah star, because according to our best measurements, this star is older than the universe itself. Let that sit for a moment. The universe is 13.8 billion years old. We know this with extraordinary precision. Multiple independent methods, cross-checked, verified, nailed down to within 1%. And this one star? 14.5 billion years. 700 million years before the Big Bang. That's not a rounding error. That's a crime scene. So let's open the case file. Exhibit A, 1912, Mount Wilson Observatory, California. Astronomer W.S. Adams notices something strange about this star. It's moving fast, unusually fast, 170 kilometers per second across the sky. Stars in our neighborhood don't move like that. This one is passing through, a visitor from somewhere much older. For decades, nobody thinks much of it. Just a fast star. Then, 1951, Joseph Chamberlain and Lawrence Aller take a closer look at its light. They split it into a spectrum and find almost nothing. The star is made of hydrogen and helium and practically nothing else. Its iron content is less than 0.5% of the sun's. This is a fingerprint. In the early universe, there was no iron, no carbon, no oxygen, just hydrogen and helium forged in the Big Bang. Heavier elements came later, cooked inside stars, scattered by supernovae, generation after generation. A star with almost no metals is a star born before most of those generations happened. HD 1400283 was born near the beginning, but how near? Exhibit B, 2013. Howard Bond and a team of astronomers aimed the Hubble Space Telescope at Methuselah. Not to photograph it, to measure its distance with extreme precision, parallax. They watch how it shifts against background stars as Earth orbits the Sun. They nail it down, 190.1 light-years, plus or minus 0.6 of a light-year. That's like measuring the distance from New York to London and being off by 3 meters. With the distance lot, they feed the data into stellar evolution models, temperature, luminosity, chemical composition, and the model spits out an age. 14.46 billion years, plus or minus 800 million. The best estimate is 700 million years older than the universe. The error bars, that 800 million year window, technically allow the star to be younger than the universe, just barely. At the very edge of the margin. But the central value, the most likely answer, says this star was born before there was anything to be born in. That's the paradox, and it doesn't go away easily. Exhibit C, the investigation. First suspect, the distance. If Methuselah is closer than we think, it's dimmer than we think, and the age model shift. But Hubble's parallax measurement is one of the most precise we've ever done. You can't shave off 700 million years by tweaking the distance. Second suspect, the stellar models. Stars are not simple objects. Their interiors involve turbulent convection, nuclear reaction rates, element diffusion, processes we model with assumptions and approximations. Change one assumption and the age shifts. In 2024, a team from Liège tried exactly this. They built custom stellar models using Methuselah's actual chemical composition, not solar-scaled estimates, but the real measured abundances of oxygen, magnesium, and calcium. With those tailored models, the age dropped to 12.3 billion years. Problem solved? Not quite. The answer depends entirely on which abundances you trust. Different measurements give different ages. 12 billion, 13, 14. The model is sensitive, too sensitive. Change the oxygen abundance by 20% and the age swings by 2 billion years. That's not a measurement. That's a confession that we don't fully understand what's happening inside this star. Third suspect, something we can't see, stellar mergers, mass transfer from a companion that has since died. Events that would have altered the star's evolution in ways that make it look older than it is. There's no direct evidence for this, but absence of evidence is not evidence of absence. And then, 2025, new evidence. The team used TESS, the Transiting Exoplanet Survey satellite, to listen to Methuselah. Not for planets, for vibrations. Stars ring like bells, and the frequency of those oscillations reveals their internal structure. This is astroseismology, stellar forensics. They detected 6 radial modes and 11 dipolar mixed modes. From those vibrations, they measured the mass, 0.75 solar masses, the radius, 2.078 times the sun, and the age, 14.2 billion years, plus or minus 400 million. The error bar shrank, the age didn't. The star is still, most likely, older than the universe, and the best tool we have, one that probes the interior of the star, not just its surface, confirms it. Case file still open. Now Methuselah is not alone. 6,000 light-years away, there's a star called SMSSJ0313. It has 10 million times less iron than the Sun. It formed about 200 million years after the Big Bang, from gas enriched by one of the very first supernovae in cosmic history. We're looking at a second-generation star, a star whose parent was among the first objects that ever existed. We've never seen those first stars directly. Population 3, they're called. Born from pure hydrogen and helium, massive, short-lived, gone before the universe was 1 billion years old. But their children are still here, silent witnesses to an era we can't observe. And one of those witnesses, Methuselah, is telling us something doesn't add up. Either the star is younger than it looks, and we don't fully understand stellar physics, or the universe is slightly older than we think, and our cosmological models need adjustment. Or something happened to this star, something we haven't discovered yet, that rewrote its clock. Every answer opens a new question. This is the thing about science at the edge. We built instruments precise enough to measure the age of the universe to within 1%. We built models sophisticated enough to date individual stars. And when we compare the two answers, they don't quite match. The tools are extraordinary. The disagreement is real. The case file on HD 1400283 remains open. It's been open for over a century. Every few years, someone adds a new page, a better measurement, a refined model, a new technique. And every time, the star pushes back. Not enough to break anything, just enough to remind us that the universe keeps its oldest secrets very carefully. Somewhere in Libra, a dim star drifts through the Milky Way at 170 kilometers per second. It has been drifting since before everything. And it will keep drifting long after we close the file. This is Stardrift FM. Keep drifting.